This program is a presentation of UCTV for educational and non-commercial use only.
What I'd like to do for the introduction is talk to you a little bit about the center that we have here that is part of the Institute that is concentrating, focusing its efforts on integrated energy efficient design. The center has several topics that it's interested in on the side of, let's say, applications in energy efficiency. On the top left, you're seeing an integrated building. This is courtesy of our partners from the United Technologies Corporation. You're seeing a building within which people are moving around, air conditioning, cooling, heating, lights, data centers. Everything is working together to make our life hard in the context of energy reduction. On the left, you're seeing a diesel engine from Ford. Suddenly, the new mandate on energy efficiency is going to provide for a lot of work inside the automotive industry in order to try to meet that at 35 gallons as it's now set into law. Energy storage is one of the outstanding problems in electric power grid context. Energy harvesting and micropower off-grid generation. Data center cooling that we are working on with our colleagues in the computer science department. And also last but not least, the issue of the smart grid. How do we make the grid smart, efficient, so that we waste as little of the energy as we can? Our purpose and way of doing things is quite interdisciplinary. The faculty that we have within the center span a huge range of topics, starting from controls to dynamics, dynamical systems, to computer science, to microfluidics and sensors, when you want to measure, for example, whether your energy efficient design is also bringing discomfort to people inside a building. You want things like CO2 and humidity sensors. It has 2 National Academy members, 3 Sloan Fellows, numerous other awards. And it is a context within which research and development in energy efficiency can be done. So on this slide, I'd like to present sort of the core idea of what the capabilities are. Sometimes the issues in computation and control are somewhat hidden, and you don't see them very well, but if you just take a look at your cell phone, the reason why it's so small is essentially because of an algorithm. It is hidden, that part of the issue, but it's in some sense visible in size, or rather invisible in size. US buildings produce 48% of carbon emissions, and I'm sure everybody in this room actually knows these numbers. I still get a chill every time I look at them. 71% of US electricity, and so on and so forth. Buildings also constitute sources of large pollution, like the one on the left from an industrial plant. Our center is trying to think about what the core causes of these kinds of things are, and how can we affect these core causes in order to change the situation. What I've shown you on the right is actually a simulation from a recent collaboration that we had with Princeton and some colleagues at the Royal Institute in Sweden, where we have taken one of these plumes and then reconstituted it in its core components, so that perhaps you can take a look at one of these core components and say, let me see how I can actually diminish that output of CO2 by hitting at the core of what the spread is. What are we trying to do and why does it matter? Here is the split of commercial energy and usage. Lighting leads, space heating, space cooling are big items. But there is another perspective, and that is that, and this is from our colleagues at the Lawrence Berkeley National Lab, and that is that the building is really an integrated system. It has all these components like the cooling towers, fuel cells, roofs, PV panels, and so on and so forth, variable air volume boxes, and down at this corner of it is the integrated controls with real-time modeling, fault diagnostics, and optimization. In some sense, in this point in time, this is a little bit of a dream. You really don't have a unified set of algorithms for control and computation of this kind of thing, where the building can be made very, very efficient so that the different sides of the building don't fight each other when they operate. How well can we do? Can we do 70% better in new buildings, 90% better, 50% better in retrofits? There are certain things that you can do that are going to bring you to 20 to 30% almost immediately. What are the kind of things that are going to usher in these kinds of numbers? Well, one part of it is an integrated design. How is it done today? What are the limitations of current practice? Here is a report from NREL on 6 different really high-end buildings in which an attempt has been made to do a net zero energy design. This one is quite unique at the Zion National Park. Down here. The unfortunate conclusion of the study is that all of these buildings actually underperformed by 25 to 75%. And the basic reasons for this are stated verbatim in small caps, and then I sort of emphasized a couple of quotes for the purpose of indicating that almost all of the reasons for underperformance of these buildings was within the need of integrated design. Uncertainties, design teams were too optimistic about the how the occupants would behave, plug loads were often greater than design predictions, and so on and so forth. This is the piece that engineering can solve, good engineering can solve in the long term. But it's not just for the unique buildings. Actually, to some extent, there are a lot of buildings that are coming up that are not unique in any way or form. We need to understand what kind of a design do we need to have for, let's say, a zero energy building. What is new in the approach that we are taking here, and why do we think it's going to be successful? The current efforts give you a little bit of a dashboard kind of a picture like you have in Prius as far as the energy consumption in your home, or perhaps energy consumption in a large building is concerned. Let's think about energy efficiency cruise control in this context, in which the occupants are actually not required to pay attention 24/7 to the exact behavior of the system, but the system can perhaps self-tune and self-commission. For that, we need best components and best integration tools. And we also need to look broader. We need to look out of the building and into the whole power grid. And I'm going to talk a little bit about it in a second. We had a program here for the last couple of years, and in collaboration with United Technologies, within which we have studied problems of similar complexity, sponsored by DARPA. The uncertainty, as I pointed out in the design of these previous buildings, was one of the key problems in design, engineering design. We have developed a range of tools that enable us to manage that complexity. There are tools like those that tell you how to change a communication protocol without affecting the whole system. There are tools that tell you how to prevent the system into going in unwanted oscillation. It is a fact that most of the systems of cooling and heating actually go into unwanted oscillation that prevent them from operating at an optimal point, and you're losing quite a bit of energy because of these fluctuations. There are tools that are also going to be able to give you prediction as to what are the optimal types of things to do in order to make the whole system energy efficient. And we're talking here about tools that can deal with thousands and thousands of components and thousands and thousands of uncertain variables. Just briefly, we do worry about adding alternative sources to classical energy sources. We model those, and we want to stay within this blue trajectory that is inside that picture, that is not only energy efficient, but safe, as opposed to the red one. And we can compute these things very efficiently. In summary, this is a picture in which, a movie in which the air conditioning is turned on and then the window closes up because there was sensing that was done that said, well, the window is open and air conditioning is on, and that's wasting energy. If you think about it, that should be a pretty simple thing to do. One part of the system communicates to the other that, the window is open and air conditioning is on, so therefore turn it off. It might not be that simple. The outside air might actually be cooler than the inside in the evening. You might need to measure a little bit more than just the fact that the two systems are turned on at the same time, and you need some kind of an integrated brain inside the building to tell it that perhaps joint effects of air conditioning, a little bit of air conditioning, and a little bit of outside air is going to do better than just any single component together. That's one point. And then the other one is, and that actually goes into the next two talks, it is not just a home, it is not just a residential building, it is all the way out to the neighborhood scale and the power grid scale. We need to have these tools that actually are able to design better at the integrated system scale. If we want to have power from the grid to the house and vice versa, where the houses are actually producing some of the energy locally and efficiently, we need to start thinking about the integrated design of this thing now. We cannot have it done in an ad hoc way. For that purpose, we have established a sequence of relationships with various partners, funding agencies like DARPA and Department of Energy, international partnerships with people in Sweden and Asia, commercial partners such as United Technologies and Ford, and national labs, in particular, Arun Majumdar is here at the Berkeley Lab, with whom, together with United Technologies, we have one of these first seed projects on integrated design that's called HyperBrick. So with that, I'd like to introduce the next speaker. It's Jack Sahl, who is the Director of Environment and Resource Sustainability at Southern California Edison, and he's going to talk to us about electric utility sustainability and integrated systems.
So this framework here, this picture kind of shows what we consider then to be our system. And just to review, to catch people up, is we have the customer in their domain here, and the relationship with the customer is fundamentally changing, and I'll go into that a little bit more. And then you have distribution, transmission, and generation through here. The really challenging part from our industry side is the introduction of generation sources that are not fully under our control, and the introduction of customer behaviors, which we are encouraging, where they have increased choices to make with regards to the utilization of the system. The key to that is these little yellow boxes here, which is the ability to store electricity in ways that we haven't been able to do in the past in order to somehow mitigate some of the variability that's associated with this. And it's that model that I want to spend a little bit of time talking with you about today. So the evolution then of the system has been that we've gone from a system that was relatively straightforward and under control to one that incorporates a lot of different choices that both people and equipment get to make. And the key to this is the ability to send price signals to either equipment or to people so that they actually have the ability to modify their behaviors in a way that is in their best interest. But as we go forward, what we're really looking at is a set of systems and trying to find a way to manage that and to build control onto that is one of our key challenges. So then in our vocabulary, the way that we talk about that is through these 5 sorts of interconnecting systems. It starts with us with regards to customers and the customers making specific solutions or specific decisions about how they're going to operate. And I think both the next speaker and then tomorrow, Nancy Jenkins from our organization will be addressing that issue in much more detail than I will be. Smart metering gives the capability of both to provide an interface between the home area networks that will be created and also the ability for this metering system to interface with our systems on the distribution transmission side. I will say a little bit about, but not spend too much time on how all of this is going to change the fundamental nature of what our workforce is going to look like, because the tools and the needs and the capabilities of the workforce of the future has to be able to match the technologies and the systems that we have in the future. And then the grid control, asset optimization, and then the construction of the energy efficient renewables and storage capability. So when we refer to a smart grid, we're referring to how the whole system then comes together and works together. The household of the future then is looking like a series of capabilities both within the appliances that you get and also the information that you're getting from those appliances with regards to how you're going to operate in the future, and a series of additional distributed generation capabilities and battery storage capabilities within the house, helping to manage things like the plug-in hybrid vehicles. And this then becomes the real driving source of a lot of the change that has to be made. Now, much of this technology isn't where we want it today. Specifically, the home energy storage systems are still something that needs to be worked on and developed. And the hope for the plug-in electric vehicles is still not fully realized. But the ability to manage when you charge the vehicles and the ability for those vehicles to form as storage systems for the house is something that is integral to making this work. The metering and the ability to get feedback both ways on that system, both into the house and into you as a customer, and going back into the distribution system, is going to be key to this success. This is a slide that shows the electricity consumption per capita over time down here, electricity up here. And the reason I put this up here is to emphasize that the energy efficiency programs can work, and we have a real strong track record in California of getting really good success from those. And that's why, from a foundational perspective and from an opportunity for us to make real progress going forward, this provides us with an exciting possibility for us to meet some of these challenges that we've been talking about today. This is the energy crisis of the 70s, and at that point there were a whole host of initiatives designed to create both alternative energies and energy efficiencies. And this is the trajectory of the line of California after that, and this is the trajectory of the line in the United States after that. And it's a very encouraging set of information to be able to see what can be done if you get the alignment, as Commissioner Grunig was speaking of, if you get the alignment of policy along with the RD&D that needs to be done, and the activities of private industry and your customers in order to embrace these kind of activities. And so I just want to emphasize the importance of and the ability for us to be very successful in regards to energy efficiency and demand response. As we have talked about, the problem then becomes one of how do you integrate these systems here, where you're no longer speaking of a house, but you're now speaking of neighborhoods, and that's then what we're trying to go ahead and address. So this slide here depicts what we're looking for in terms of the technologies that are now on the generation, on the transmission side. And what we really are looking to try and do is both change the environmental footprint of the generation so that you can address those kind of global needs. But also, what a consequence of that is that you end up with a set of systems that instead of having a handful of generation sources, you will literally have millions of generation sources. And integrating that back into the system so you still have the reliable and economic power becomes a real challenging. Again, we're optimistic that these systems can come together and function in a rational way, but that still is a challenge yet to be addressed. So the kind of things then that we're struggling with and that we're trying to address are to get more data management and more data collection throughout the whole system so that you have efficiencies that are built into this, but also so that you have better command and control of those capabilities. And then beyond the transmission, you then have to move, because you have so much interface going on within from the customer side, the substation will become a source of a lot of this activity. And again, notice the ability to have some amount of controls that are in that area, and also some ability to do distributed generation on this side, and also battery storage. Finally, last point down here is that if all this is going to make sense, all of your transmission and your household activities will make sense, you also then have to change the way that you run a distribution circuit, and so that you can manage it at the local level. And that's, again, is a very exciting aspect of this for us, is how you tie that together. This is an example, or a cartoon, if you would, of speaking about what we call our circuit of the future, and how the distribution circuit is changing. Instead of being one that is basically providing power at will, it has a lot more command and control capabilities. It has a lot more ability to reroute and to sense where faults are, the ability to repair itself without line crews going out to do that function, is all part of this idea of the circuit of the future. When you move back up to the transmission side, you're talking about very large amounts of power that are being pushed around. And one of the activities that's at the national level is to tie the grid together so that you can find generation sources that are, say, wind or solar generation that are in one part of the country can be used to achieve reliabilities of those generations in another part of the country. But in order to do that, we're going to need to have the transmission system connected in a better way than has been historically. The systems and the layering of the systems are really designed to do a couple of things on the transmission side. But one of the key things is to given the variability that's inherent in these new systems, to prevent catastrophic failures that cause the large-scale blackouts that we've experienced in the northeast part of the United States. And so part of the advantage of these grid control systems are the smart grid. In addition to the efficiencies that you get, you also get the ability to manage system failures. And this also then moves down from both the transmission side down into to the distribution side. One of our highest priorities consistently is to provide reliable electric power, because it's so important from a customer's perspective to know that there will be electricity available, and so people can use it when they need to use it. And so there are a variety of approaches that are to address that, all of which are part of the concept of the smart grid. Again, Nancy Jenkins later will be talking more about the customer side, but I did want to focus on the advantages that are coming with regards to meters that are much more capable of interfacing with people, interfacing with equipment that's within their systems. But I think most importantly, from an environmental perspective, the smart metering capability will provide price signals, and these price signals will give an opportunity for people to make more conscious decisions about when they want to use electricity and when they don't. And I think it'll drive behaviors that will be positive in terms of where we're trying to go forward. And so there'll be a combination of both new sorts of information, which is more similar to what you saw on the Prius in terms of your energy usage, and also there'll be the ability for you to interface with your smart appliances as well. Part of the difficulty of doing all this in a rational sort of way relates to trying to plan for the generation, because as we've worked back up the system from the customer through distribution transmission, at some level you have to have a generation planning scenario. And I'm throwing in this slide to represent sometimes just how difficult that can be. This black line was our peak load, system peak load over this time frame, and things started happening this last year because of the economic situation that substantially changed that. And you can see our different scenarios have changed substantially over the time. And right now we're going through a time where our peak load is not expected to grow this year or next, but it will again do this trajectory. But if it takes a number of years, up to 5 to 10 years, to get generation online, that means then that we have to start on that planning process for peak loads that are out in these years currently. And it's made a more difficult challenge by the fact that introducing new technologies like wind and solar at utility scale that are not under our direct control means that sometimes the peak capability has to be more than the planned peak load. There are a lot of challenges with regards to meeting the efficient and resource efficient and sustainable generation. We're currently at 16% in terms of where we are as a utility. There are a number of initiatives to try to get to, I think the number is going to end up being around 33% by 2020. And there are a variety of different things that are in place with this. It's a substantially different environment now with the change in administration in Washington, and so I don't think it's going to be a situation where California is making these initiatives independent of the federal activities, and I think you're going to see an increased evolution between both what's going on in California at the federal level and at the international level. But it's a very large challenge both to meet the renewable portfolio standards and also try and provide for the continual system load increases as well, while trying to keep the rates at a reasonable level. This, I think, is a particularly promising option for us, and this is as opposed to household solar, this is what we call utility scale rooftop solar. This is a warehouse in out by Ontario Airport. And if you've been out there, you realize that there's a lot of logistics terminals out there, and it's a very large set of these kind of roofs that are available. Putting solar power plants on top of these kind of roofs have a number of advantages, one of which is that the solar is directly where one of our peak load areas is, which is in the inland part of our communities. But in addition to that, you don't have to impact land in the deserts or other areas, because you're basically using an unused space at the top of the roof. But you also have advantages that you don't have line losses associated with transmission, because the system here goes directly into our distribution system. So there will be a large amount of these type of urban rooftop solar utility scale systems, which I think will go a long way to make the whole system much more efficient and much more easy to be managed. I did want to mention just a few comments about the changes that we're talking about will require changes in our workforce, in that whether or not it's the role of the engineer or the role of the line crews or our grid operators or the system planners, they all will have a much more complicated set of activities in terms of what they're trying to manage to and what the kind of activities that they have to take responsibility for. It's an exciting opportunity, clearly, but it's not at all comfortable for some of our current workforce to see some of the innovation that's coming in, because they're going to have to retool in order to be able to be as effective in this work environment. Another opportunity that some of this technology provides is the ability for us to work at a safer level, and this is very important to us in our industry. And there's a lot of this technology and a lot of the stuff that will be coming forward, which provides a much higher level of safety for all of our organizations, and I think that'll be an additional advantage as well. And in addition to that, I think there's going to be some productivity improvements in terms of just greater use of computer command and controls and those kind of systems. So finally, this is a slide or a cartoon that tries to summarize the high-level conversation that I've kind of led us through, in that what we're trying to do is integrate a variety of systems that historically operated in their own individual silos. So whether or not it's the generation side or the customer side in terms of getting the energy efficiency, the transmission side, our internal operations in terms of trying to get our supply chain, our fleet, our buildings, and then the utilization of IT to tie all this stuff together is the system of systems that we're working on. This won't be something that can be done without good partnerships in our communities, both at the planning level and also at the regulatory level, to make sure all this stuff happens. And clearly it won't happen unless you have a very healthy RD&D machine, which is continuing to put out the kind of solutions that are ready to be tested, or not tested, but deployed in this sort of environment. And what we're ultimately looking for, though, is to once again provide safe, reliable, economic, and sustainable electricity for our customers. With that, I will close, and if I have time for questions, I'll take a few questions.
Well, first of all, it's a pleasure to be here. I did graduate from this campus, so it's a pleasure to be back and have the opportunity to speak to you here. I'm going to be speaking about some content that has a fair amount of similarity with what the last couple of speakers discussed, so I'll go through some of the common material pretty quickly and not repeat that. Before getting into the content, just for those of you who may not be aware, the two Sempra energy utilities are San Diego Gas and Electric and Southern California Gas Company. SDG&E is the smallest of the three investor-owned utilities with 1.3 million customers down in the San Diego region there. Southern California Gas Company is the largest natural gas distribution company in the U.S. with 5 million meters extending from around San Luis Obispo all the way down. So this picture here depicts a view. It relates largely to smart grid, as you were just hearing about, slightly different graphic, and I'll try and add a little bit of additional perspective to what you just heard about. First of all, one of the main things we see about the energy future as it's evolving is that from today, where we have largely one-way flows of information and energy, information flowing from customers back to us through meter reads, billing them, energy flowing from us to them. In the future, throughout the grid at all scales, from large central systems, as you see on the left side of this graph, all the way out to the homes and businesses with small-scale resources, we see in the future that we'll have two-way flows of energy and two-way flows of communication that together will actually enable this whole concept of zero net that we'll be talking about a little bit. Let me address also a couple things. The question of cost for the smart grid was just mentioned. All three of the investor-owned utilities in California are deploying smart meter systems. Those deployments will be complete by 2011 to 2013, depending on schedules. That's the first piece you could think of the smart grid. That's the sort of foundation upon which that's built. The cost of those systems is between $100 and a couple of $100 per customer. I've heard current estimates for deploying smart grid, depending on how much total functionality there is, from $700 per meter up to $2,500. And that depends a lot on how fast technology evolves and how the cost and performance curves of some of these components comes down. So it's very central to some of the discussion today. Many of the components and devices that were discussed are sub-elements that will not just go into people's homes and businesses, but also will be deployed out in the grid to support sensing and communicating. And then inside the home. So the concept of smart home has already been discussed. So what you see here is a slightly different depiction of that smart home. As far as timing is concerned, we haven't talked too much about that. As I said, the smart grid deployments have already begun, the smart meter deployments have already begun and will be completed over the next 2 or 3 years. Time estimates to achieve smart home, smart grid functionality range between probably 10 to 20 years, depending. The stimulus funding has increased dramatically, the interest in smart grid, and I think it's also changed people's perspectives on timelines. So now with the stimulus and the raise in awareness and urgency around this, people are talking about moving faster. But the timing of the smart grid actually will dictate to a certain degree the timing of zero net, because this energy infrastructure that we were talking about here, in order to enable zero net, to the extent that we don't mean that on a building by building basis, so that each building needs to generate and store its own energy, requires actually that there's an ability to flow information and power across the grid at scales that are much smaller than we currently have on the system. So smart grid and zero net kind of go hand in hand. At this point in time, the initial demonstrations of community scale microgrids, so at the neighborhood level, are just beginning. The stimulus program will fund 8 regional demonstrations at up to about $100 million each. So that will be a way of demonstrating full end-to-end functionality for smart grid capability. At the present time, there's 4 or 5 smart grid demonstrations that have already begun across the country, but I think the point is that we're still at the foundation stage with this functionality. One important point for the Institute here and all the people here that are involved in energy efficiency is that the priority of energy efficiency in state policy is actually mandated in CPUC policy, actually state energy policy that was put in place, I believe it was 2004 when this was enacted, but the Energy Commission and the CPUC established a loading order or a preference order in which resources should be procured or deployed, and energy efficiency is at the very top. So when selecting resources from a policy point of view, utilities are required to first look to energy efficiency, next to renewables, following that clean fossil, and everything else down the line. The role of utilities in energy efficiency, Commissioner Grunich talked quite a bit about the state strategic plan and the role of utilities, but fundamentally, our role is to operationalize the state's policies on energy efficiency by first supporting introduction of new technologies through identification, testing, piloting, and sponsored R&D, and then once technologies come into the pipeline, to promote adoption with customers through education and through administering incentives to customers for those adoptions. And in some sense, we look at this as acting as the agent for customers in aggregate to identify promising technologies and helping make sure that in context of what Commissioner Grunich was saying, that we help promote rational economic decisions, meaning that 6-month paybacks will pretty much keep most technologies out of the market, and through incentive programs, education, and other active outreach programs, we seek to get adoption on a longer-term payback. Track record in the state has been outstanding, as you've seen from the per capita energy curves, and I don't know what that would be on a normalized basis, but I think we probably achieved something like 30 to 50% reduction relative to some business as usual base case. These 4 big, bold strategies, as Commissioner Grunich referred to them, have already been discussed. It puts a time point on the goal in the state for zero net energy at the commercial and residential scales. So as was mentioned before, the goal is for zero net at the residential level for new construction in 2020 and for commercial in 2030. In addition, although the state doesn't have a goal for overall net zero, federal government has a carbon neutral goal of 2030, and for commercial buildings has established 2050 as the point in time for complete zero net for commercial buildings. So formatting is a little bit off on this chart, but what it does emphasize is that the best designs today are about twice as efficient as the installed capital base that we have. So depending on what the average age of a building would be, say 10 to 20 years, this is showing that we're reducing energy consumption or improving energy efficiency by 50% about every 15 years or so. So if we were to continue that goal or that progress, this goal of zero net by 2020, you can see we'd be about halfway there with the pure energy efficiency pieces, leaving the other half to come from distributed energy resources. I think most of this has been covered in previous discussions, but the elements, the building blocks, and I think we need to use all of them to achieve the goals, but energy management and the smart home, I think, are a very important piece of it. The smart home, as has been discussed in the last few presentations, actually, by controlling devices, even at their current efficiency, people estimate in the range of 15% reduction in energy use is possible. Interesting regarding the discussion about consumer behavior, the limited research that's been done in that regard indicates that, at least for your average residential customer, there's a sort of a novelty effect where people will pay close attention to an energy display and make significant changes in how they use energy for a period of time, depending on the customer, but a few weeks, a month, or something like that, and then eventually the novelty wears off and they sort of go back to different behaviors. So what probably is necessary for all of this to work and achieve the goals, as I think has been discussed, is to be able to make this relatively invisible to customers, so that over time, home automation for most people will be adopted because of comfort, convenience, entertainment, and these types of things. The energy management piece of it, for most, needs to be put in the background, programmed with smart devices and logic so that they don't really need to intervene and the buildings operate in an automated way. Then efficient building envelope, a lot of discussion this morning about lighting. Commissioner Grunich mentioned HVAC as another big piece of this, and then the renewable energy and other distributed energy resources, and finally, intelligent design tools. So this topic of the session here was efficient building, so I did want to show a couple of examples of technologies that show a lot of promise. Cool roofs, windows, and insulation will be critical. One of the promising points is that cool roofs and various types of window design are retrofittable, so those will probably be a significant part of the retrofit solution, in addition to retrofit insulation and then adoption of smart appliances as those become available. So I already talked a little bit about this. I think that in order to get to a zero net within 10 years or even 15, 20 years, this distributed generation and energy storage is a very big piece of it. So, one question would be, if you look at 2020 as your time point, are we likely to get there? I think for new construction, certainly that's possible. But looking at the adoption of photovoltaics in the state and projecting that forward, in the 2020 timeframe, we'll probably be in the range of 10 to 15% of the households with solar. So, I don't think we're going to be getting close to 100% zero net, but even this, even say 10% of the households would be a pretty significant accomplishment by that time frame. Shown here are a whole collection of adoption curves for things. I think this is probably related to a certain extent to the question of photovoltaics, but also relates to smart home functionality, how fast people will adopt it. Most of the functionality that you've seen in the different presentations today exists at a either prototype or early commercial stage. So you can find today full smart home setups at a demonstration level. But this, if you look at all these different adoption curves, they tend to show that, for the very most rapidly adopted consumer-related devices, 5 years would be the absolute fastest. Sort of TV was adopted in a time frame like that. But most of these are in the 10 years on average, up to 20 years or so. So part of this is as it comes to voluntary consumer adoption, is being realistic about what the uptake rates are going to be with people. And the last point here on policy flexibility is that and as Commissioner Grunich mentioned, as we see how technology is evolving and see what consumer behavior is, look at this in terms of a feedback loop and have some policy flexibility in what points in time we establish goals and mandates and adjust them if needed. So on the whole topic of zero net, there is the question of at what scale. And certainly if you mandate or target zero net at the individual building level, you tend to be prescribing technologies, you're prescribing scale, and there's only so many ways in which you can achieve zero net at the building level. So the question is, how far do we go? There's a lot of effort right now on microgrids and things of that nature to have zero net at the community level. That probably makes significant sense. But then at the regional level, certainly the central station renewable resources that were discussed in the prior presentation are an important part of the solution. As they become more cost effective, they also help make all of this energy ecology cost effective. So I think zero net also needs to be viewed at least at the regional level. And we need to focus on the ends of low environmental footprint and efficient use of energy and have some flexibility in definition of zero net. We should let technology and economics drive exactly what the average scale for this zero net. And smart grid is critical to all this because the smart grid will enable flows of energy at virtually all scales, from regional down to smallest. I heard a term this week for the first time, nanogrid, which means building. So either nanogrid or building, your choice. So what are the keys to success? Critical to this type of forum, an innovation pipeline is very, very critical. And to support that, the universities and venture capitalists are extremely important. And to direct the right kind of effort, in the earlier discussion with Commissioner Grunick, it was discussed about, are we going to sustain this? There have been instances of alternate fuel vehicles, even the original foray into renewable energy, where the policy didn't sustain long enough to really have the energy take hold, or the industry take hold. So first is focus, and in the area of energy efficiency, of course, climate change policy is becoming pretty well entrenched. There could be a reversion, but I think it's looking less likely. A lot of focus on energy independence, so that provides focus. Funding is critical as well. A big, big piece of the stimulus package is related to energy efficiency. And then to minimize the cycle time on development and deployment of technologies, and the green ones are places where the utilities play into this. A big part of what we're charged with by the Commission is to work with universities, entrepreneurs, other parties to help demonstrate and commercialize the technologies. Then the other piece is consumer adoption, where education and outreach is critical. Incentives, because as has been discussed, people tend to be somewhat, tend to require much shorter payback terms than pure economics might often dictate, so incentives become important. Standards, certainly for new buildings, and then just, there is a natural soak time for the general public to sort of get used to things and start adopting them. And I already talked about this importance of flexible policy. If you look at climate change policy, policy on renewables, energy efficiency, all the things, smart grid too, there's this trade-off of, do we need to set an ambitious goal and say we're going to have a complete smart grid by 2015 or 2020, establish that as a target, but recognize that the cost and performance curves of these technologies, even with focus and funding, may not be exactly 2015, maybe it's 2017. So we're big advocates of a little bit of policy flexibility. That's it.
there's a fascinating chart you showed where you list sort of history of consumer adoption of various pieces of technology. And I'm not sure if I have a question or a food for thought, but it strikes me that most of the items on there are in some sense very discretionary. And I'm wondering if you guys have looked at what kind of proxies you have where the adoption is in some sense regulatory driven or much more financially driven than consumer preference driven.
It's a good point. I think the smart home in total, a good portion of it will be discretionary, I'm sure, because it's more likely going to be comfort and entertainment and things like that and have some energy along with it. But yeah, things like fuel, fleet average fuel economy, building code, things like that, you can look at as well, where a particular timeline is put out. We could drive that to be faster, and I think within this broader area, it is a combination of standards, mandatory aspects, and voluntary ones. So we have renewable portfolio standard, greenhouse gas cap; those are mandatory. There's going to be building standards put in place, but a fair amount of this in-home piece is going to be behavioral or voluntary. To get rapid adoption, it may be that significant incentives are required, and also that parties, utilities or third parties, take a lot of the headache away from the consumer and just put in a simple, basic functionality type of energy management system, issue A, and program it for them, and because left to itself, if people talk about 2020, so roughly a 10-year time frame, it seems long, but it's really not. If you look at some of these and consider that somebody's desire to have a PC is probably more than to have a refrigerator cycling device or something like that.
Regarding plug-in hybrids and the grid, any way to say whether the current grid is capable of supplying the power needs to provide the recharging necessary for a plug-in hybrid car?
I've seen various estimates on that. There's the issue of capacity on the grid, but also time of use. But assuming that vehicles charge off-peak, I've read a statistic that said 73% of demand for an entire U.S. auto fleet, 73% of the demand for that could be met with generation resources that we already have. So a big part of that is putting in rate structures and automation that allow the vehicles to actually be charged off-peak. Because if they're charging on peak, another sort of factoid I've heard is that 2 vehicles will require a transformer upgrade on the distribution system if they're charging simultaneously. So again, there's a lot of innovation that can go on in terms of how that vehicle charging is automated, and I think there's a lot of opportunity to cross-share between some of the basic device level research that's been discussed here that may have one application in mind but can go cross. Another thing I forgot to mention during my discussion, energy efficiency on the transmission and distribution grid itself, particularly distribution, is something that interested people should take a look at that are working in this domain, because 10, 12, 15% of the energy produced is lost in delivery, and there is a lot of automation and control that can happen at the distribution level that can reduce that number. So as you kind of think about energy efficiency overall, beyond the buildings, think about perhaps the grid itself.
Thank you. Unlike Solar Edison or PG&E, so Sempra is in a unique position to utilize the gas as energy resources. What do you think about the usage of the gas in the context of smart house in the future?
Say it again, please.
How do you think about the usage of the gas in the context of the smart home?
Utilization of natural gas in the context of smart home?
Yes, please.
Well, we see natural gas as the cleanest among fossil fuels and an important part of bridging to whatever the future energy solutions may be. So what we are focused on currently in terms of our R&D activities in that domain is energy efficiency, so meaning, reduce natural gas and electricity use through technology, and then ultra-high efficient devices, so that, although natural gas is a fossil fuel, it's relatively clean, and we're focused on very highly efficient end-use devices to use it.
If you fast forward your smart grid vision, say 5, 10, 15 years, and you have this, incredibly large capacity in terms of distributed energy across smart homes, smart enterprise, and so forth, what happens to the role of a utility, and how does your business model change fundamentally?
Well, I think that's the $63,000 question. It's something that we think a lot about. I think, over a 30-year horizon or so, and most anybody I've, talked to or listened to, certainly from the core functions of distribution of gas and electricity, I think that stays. Most visions of the smart grid, zero net or not, envision that there needs to be the ability to move power from, wholesale layer to residential and back. So I think, the transmission and distribution function of the utility is probably going to be necessary for the foreseeable future. How we support end use, customers, smart homes, smart business, electric vehicles, all those things I think are going to be, the policies in those regards are going to be set over the next several years. Right now, it's anybody's guess, really. What does Obama do when he's done?
Sorry?
What does Obama do when he's done?
Any other
Thank you very
questions?
much.